Hi, my name is Assam Khalid, and today I'm going to present the final product of data-driven security and privacy. Problem statement is creating the deepfakes images, uh, generated by different methods. The most popular ones are autoencoder and generative adversarial networks. So, there are a lot of different methods that are proposed by researchers to detect the deepfake images, but these methods require a huge amount of training real and fake images datasets. Like in the real world, this is not feasible as we don't have enough amount of labeled fake images datasets. So I try to solve this problem in two different approaches. One is one class classification based, that is using only the real images to train my model on and then detecting the deepfakes. And the other method is supervised learning based binary classification methods, which is also like both these methods use the variation autoencoder, but the only difference is with the approaches that I use to detect the defects. So the model architecture is same as variation encoder, but the difference is with the loss function in both of these models. So the datasets I used is MNIST for as a baseline dataset to check my model is learning or not. And then I use the face forensics high quality dataset, and I use only the so I tested my model on near test dataset. So yes, I I'm trying to detect the train my model on the real images and then detecting the fake and real uh, based on the reconstruction of the variation encoder. So for the first approach, um, so I train my model only on the real images, and then after training, the autoencoder actually learns how to reconstruct the real images in a better manner, and then during the testing time, the autoencoder knows how to reconstruct the real images better, and when the fake images are given, it reconstructs in the autoencoder reconstructs them in a bad way and giving a high reconstruction loss. And so based on that, during the testing time, I actually come up for example, if I am using 1,000 images real and 1,000 images of fake, I have 2 distributions for real and fake one, and I set up an optimal threshold to separate out these two distributions, and based on the threshold value, I compute the accuracy or the FN score. So the loss function for the vanilla or basic outgoing version autoencoder is mean square error plus scale divergence. But in my approach, I used the SSIM score as well, which is structural similarity indexing method. So the final loss function includes these three terms in this approach. So what really happens is, as I explained before, so based on during the testing time, based on the reconstruction loss of reconstruction distributions of real and fake images, I set up a threshold value. So basically, I use another sampled version of real images, and I can do the reconstruction distributions on those real images, and then take a percentile or intent quartile range of four different values, which is 80th percent, 85, 90th, and 95. And then based on which threshold gives me the best accuracy, I am reporting the results. So for the administrator sets, I was able to achieve, well, my model was able to achieve 99.6% FN score. For the neural tested dataset, the model was able to achieve 91.40 accuracy. And this is the histogram for neural textures. As you can see, this green histogram or these green lines it represents the real images distribution, and the red one shows the fake images distribution. And the threshold value actually splits these two distribution into parts, and then based on that threshold value, I compute these F1 scores. So yeah, this was the first approach, and keep in mind that I only use real images for the training, as this is a one-class classification method. For the second approach, I actually use the same model as I used in the previous model, but the only difference is with the method that I applied to like achieve my goal. So the intuition behind is that like training only on real images, same as before. But in this approach, for each mini batch, I compute the I use actually 412 real images and 100 fake images in each mini batch. So like, I like it's a supervised learning based approach. So I have the label as well. So the loss function changes a lot. Like in this approach, so I compute the L1 loss. L1 is actually the mean squared plus KLD plus SSIM, same as before. And I compute the L1 for real distribution and L1 for L2 for the fake one. It's actually the L1. And then I have this another value which I like, let's say H, and it's in the negative. So then so what's happening here is I am computing the difference between the reconstruction of real images and the fake images. If the difference is high, it means I have to like do not penalize the model, because model is trying to differentiate the real with the fake distributions. So like the loss term, the final loss becomes L1 of real plus lambda into H. Lambda is hyperparameter. You can tune these parameter based on your own experiments. So I use the value of 0.002. So if the distribution of real and fake, or the difference between these two distributions, is smaller, this HM will be like more close to zero. And when I add it here, like it will be kind of a penalizing the model. So the model will learn the difference between these two distributions more and more to like achieve the optimal uh, like convergence. And then so yeah, this is the basic intuition behind this model, and the architecture is the same. So in short, model actually learns to reconstruct the real images plus tries to learn the difference between real and fake images. So like the classification decision is made based on the same like reconstruction loss distributions as I explained in the previous approach. And yeah, I like did experiments on two datasets as I did for the first approach. So I found score for the first like for the MNIST dataset was 99.51 score. So I will show the histogram for each like after each epoch in the next slide. And for the new test, I was able to achieve 68.4% accuracy. I'm still trying to improve these results, but for now, I am able to achieve this percent accuracy. And um, yeah, so like one of the reasons is like neural test is a very hard data set, and like even though it's in a supervised learning based approach, but still model is trying to learn the fake images better, and I am using the real images better. I am using the fake images, like very small amount of fake images. So like this is the good part about this approach. So I'm not using a lot of fake images. So this is the histogram for like the for the second approach on MNIST dataset, and this is the training progress of my like the second approach after each epoch. So this is epoch 1, 0, 1, 2, and up to 5, 4, and up to 9th. So these are total 10 epochs, and you can see. So in after the first epoch, the distributions are like this: green and red. Green represents the real images, and red represents the fake one. So with each after each epoch, model is trying to differentiate or like that separate out these two distributions, and you can see up to 10th epoch model has separated them out a lot, and for up to 10th or 11th epoch I was able to achieve 98 to 99% accuracy. So yeah, these are my two approaches that I use for this final project of data driven security and privacy course. Thank you for your time. Bye.